Saxon Algebra 2, Lesson 111. Welcome back from spring break, my students. We are in an amazing place, mathematically speaking. I just grabbed Lydia's assignment sheet so we can look. We're done through the midterm. Spring break has happened. Today is the day that you don't have any homework due. That's what I mean by an extra week off. Sorry if that's confusing. We have 3 weeks of lessons. 2, 3. We are done in 3 weeks, you guys. We will have the same process for preparing for the final. We'll have a day of review, and then the final itself will be on a Thursday. We will be done, or Wednesday, sorry, I'm thinking of Tuesday, Thursday classes. But you guys are Monday, Wednesday. We'll have the review day on a Monday, May 4th. We'll have the final on May 6th. At this point, it looks like we'll do it exactly like we did the last one. I'll deliver it to your doorstep. And then we're done. By May 6th, we're done with the book. That leaves us a full month of prep time for whatever you need. The main thing I'm thinking is AccuPlacer, which is the Edmonds Community College placement test. I'm guessing Jayla may be planning running START for next year. Lydia, I'm not sure how your plans have evolved, but if you want to prepare for, and I'm not sure how that might be changing with Edmonds being closed. The community college is what I mean. Let me look into that and see what I can learn about how they're handling testing requirements for fall admission into classes. We may not have any work to do here. Thank you, Mr. COVID-19. But in any case, what I'm saying is May is a transition month that gives us time to help you prepare for whatever's coming. So we will be done with this by the 1st of May. Okay, that's good news. That's exciting news, right? Now we turn our attention to Lesson 111, which is one that most students find very manageable. 3 statements of equality. Basically what we're going to do is take our old coin problems where we have a quantity statement and a value statement. We have to figure out, how many nickels and dimes we have or something like that. And we're just going to add one more variable and then one more statement that we can turn into an equation. Let's look at the first one. There are only 2 examples. Don't you love this? 111.1, look at all those ones. Feels like a magical beginning. There were 26 nickels, dimes, and quarters in all. Okay, we recognize that. That's a quantity statement. That has nothing to do with what the coins are worth. That's just how many pieces of metal are lying on the floor. I probably told you guys this when I was in high school. I was a waitress and I got tips. And in those days, people left a lot of change in their tips. I worked at it was like a nicer version of Denny's. It was like a 24-hour, all kind, breakfast, lunch, and dinner family restaurant. And the first thing I would always do when I got home from work is I would take all the money out of my pockets. We had pockets in our little uniforms. And I would just dump all that money in the living room and then start sorting it out. And so I always imagine that act of dumping all those coins onto the floor when I'm thinking about the quantity statement. Because at that point, I didn't care how much everything was worth. I was just dumping the money out of my pockets. And there would be a big pile of coins on the floor, and that's what we're imagining. What we're seeing here in our quantity statement is that the number of nickels plus the number of dimes plus the number of quarters equals 26. Okay? This is a heads up that this is going to be a 3 statements of equality because we have 3 different kinds of coins, so we have 3 variables. There were 26 nickels, dimes, and quarters in all, and their value was $2.25. Okay, so now we can write our regular value statement. I'm writing it in terms of cents, not dollars. So 5 times the number of nickels, plus 10 times the number of dimes, that's the value of each coin, plus 25 times the number of quarters equals, their value is $2.25. So I'm making that 225 cents. How many of each type were there? if there were 10 times as many nickels as quarters. There's our third statement. Okay, so I'm just going to use an asterisk to show that this is our third statement. How many coins were there of each type if there were 10 times as many nickels as quarters? Now this is one of the ones that is confusing. We know that there are more nickels than quarters, so we're going to write the inequality first. There were 10 times as many nickels as quarters, so that means if we multiply the number of quarters times 10, that will make them equal, because there's already more nickels. So I'm just going to put the 10 over here. That's backwards. That looks like a news station, right? Q10. What is it, Q13? Yeah. So this is what's new about this problem, is that we've created a third statement of equality. I'm going to make this a 3 instead of a star. I don't like that star because that reminds me of what we used for a base equation in other problems. So I'm not going to use that. But anyway, there were 26 nickels, dimes, and quarters in all, and their value was $2.25. 5, 10, and 25 for each, the value of each coin. The total value written in cents instead of dollars, so I don't have any decimals. And then here's the last part. There were 10 times as many nickels as quarters. So there were more nickels than quarters, so we have to multiply the quarters by 10 to get them equal. Okay, now our job is to start solving this lovely set, this trio system of equations. Now, there are a number of ways that we could do this, but what we're going to do is start with this equation, because this is a nice simple variable by itself. So we're going to plug this value in for n in the other equations. So let's start it in the first one. I'm going to call them A, B, and C now, so I don't get confused. Okay, we're going to plug C into A and B. Okay, so here's the new A. It will be, oh, this should be number of nickels equals number of quarters. Sorry, I wrote that wrong. I wrote the variables wrong, but the equation's correct. So here we go, let's plug it in. 10Q, 10 times the number of quarters, this. Let me just rewrite this so we can see it better. Okay, and then this I'm going to rewrite as just 10 times NQ. I'm going to put it in the order that we like. So the number of nickels is equal to 10 times the number of quarters. So now I'm fixing the first one. 10 times the number of quarters plus the number of dimes plus the number of quarters equals 26. And then we can fix this to be, I'll put them in order that we had them before. The number of dimes plus 11 times the number of quarters equals 26. And then let's fix the second one. The number of nickels is equal to 10 times the number of quarters. So 5 times 10 times the number of quarters plus 10 times the number of dimes plus 25 times the number of quarters equals 225. There's that. Let's fix these. This will be 50 times the number of quarters, and then we can add it with this. See what I'm doing? There's 10 times the number of dimes plus 5 times 10 is 50 number of quarters plus 25, so that's 75 times the number of quarters equals 225. Okay, so far so good. I'm liking it. This is cleaned up. Now, what if we take these two, okay, these are our most current version of A and our most current version of B. Why don't we multiply this top one by minus 10 so that the D's will cancel, the dimes will cancel, right? So I'm going to multiply this one by minus 10 and write it here. This is our new A. So it'll be minus 10 times the number of dimes minus 110 times the number of quarters equals minus 260. Okay? Now, This is going to cancel because I'm going to copy the new version of b and put it right here. And that will be 10 times the number of dimes plus 75 times the number of quarters equals 225. I don't have to multiply that one by anything. Dimes up to cancel. So now I add these two. You're gone. This is going to be negative 35, right? Because the difference between these two, if it was 175, it would be 25. But it's 10 more, so it's minus 35. That's the number of quarters equals, okay, 260 minus 225. This is going to be a 5. And this is going to be a 3. And this is minus, right? Yes, because the 260 is bigger. Oh, John. So the number of quarters, I'll write it up here. Number of nickels, number of dimes, number of quarters. There will be our little answer block. And we got the number of quarters equals 1. Okay? Then we'll have to pick one of our other equations. Maybe this one looks good. I just scanned through and I was looking for ones that had quarters and something else, but only one of the other variables, and the numbers were simple. So I'm going to take this one before we multiply it by 100 and by minus 10, and I'm going to say, I'm going to work in this little box right here, the number of dimes plus 11 times the number of quarters, which is 1, equals 26. Right? This is 11, so I can subtract 11 from both sides. The number of dimes equals 15. And then they all have to add up to 26, and we've got 16 already, so the number of nickels must be 10. And I'm looking at the correct answer. Yay, we got it right. All three of these are right. Okay, so the solving is a little bit hairier because we have 3 equations, but the real difference in these problems comes in when we just have to create a third statement of equality. Okay, let's try the other one. Example 111.2. And as I recall of the homework, they really don't change very much. They don't get much more difficult than that. This one, instead of talking about coins, we're talking about, I mean, at first thought I think marbles, but they're really more like bowling balls. It just says the total number of blues, greens, and yellows in the pot was 7. Okay, so I'm imagining a big black pot like a cauldron, and inside of it are like giant and here the total number of blues, greens, and yellows in the pot was 7. That's my quantity statement. So the number of blues plus the number of greens plus the number of yellows equals 7. The blues weighed 1 pound each, the greens weighed 4 pounds each, the yellows weighed 5 pounds each, and the total weight was 25 pounds. Okay, so that's our value statement. Instead of thinking in terms of how much the coin is worth, we're thinking about how much each of these giant marbles weighs. So I'm going to go through and look at these again and write down the weight in front of each variable. So the blues weighed 1 pound each, so 1 pound for every number of blues. The greens are 4 pounds each, so I'll multiply the number of greens by 4 pounds. And the yellows are 5. And the total weight is 25 pounds. Okay? If there was one more yellow than... Okay, so there's our third statement. There's one more yellow than green, so the number of yellows is greater than the number of greens. It's by 1. It's not one more, I'm putting in mental quotes, one more means add 1. So there's one more yellow than green, so that means there's more yellows than greens, but in order to make this balance, we have to add 1 to the smaller side, and that gives us a third equation. Okay, again, there's our three statements of equality, there's our three equations, and we can use the very same approach last time. We'll start by subbing, let's call them A, B, and C now. We're going to substitute into A and B, and I didn't write this last time, let me flip this over. We plugged C into A and B, that's true, and then what we did, I don't have room to write it over there, then we eliminated, okay? So that's going to be our step one, and then two, we'll eliminate with A and B. Okay, and last time what we did, we multiplied by minus 10, the A version of our equations. So we're using both substitution and elimination, and these set themselves up nicely to eliminate first. So let's do that. We're gonna put this value for the number of yellows into those two places as well. So let's fix the first one. It's A. The number of blues plus the number of greens equals the number of greens, no, plus, sorry, I said equals, but I didn't mean it. The equal sign is after. Number of blues plus the number of greens plus the number of greens plus 1, I'll put it in parentheses so you can see that's what I substituted, equals 7. And then our second equation, we're substituting this in for that, is, this has 1 times the number of blues, I'm just going to simplify it, plus 4 times the number of greens, plus 5 times, this is where our parentheses become really important, copy the rest of the equation. Okay, so I just substituted this value in right here. Make sure to use parentheses because I have to distribute that 5 across both of those. So I have to be careful that I don't mess up that distribution. Okay, so let's fix A first. Number of blues plus the number of greens plus the number of greens plus 1. So I'm going to combine like terms here, and then I'm going to subtract 1 from both sides. So I'll have the number of blues plus 2 times the number of greens equals 6. Okay, that's just cleaning up the algebra on A. And B, let's see, let's distribute this. This would be 5 times the number of greens plus 5. So now, and I can cross that out because I've distributed it here. These two can be added as like terms, and let's subtract 5 from both sides. So I'm just doing simple algebra, but I'm kind of making it in little notes instead of writing it out completely. I hope you can follow that. Okay, so the B version becomes the number of blues plus 9 times the number of greens, right? The 4 and the 5 equals 20. Okay, I like it. John uses this notation in the book. This is his original A and B, and then he cleans them up a little bit. He puts like a little apostrophe thing, is what that's meant to be. He uses that. I haven't ever talked about that before. That's called A prime and B prime, meaning that we've changed them from their original form, but they're still basically that equation. I don't usually use that notation because I think it's nice in the book, but it looks fussy and confusing when you write it out. And mentally, I don't think it's completely necessary. We can see these as evolved forms of these. But if you've ever wondered what those little marks are in the book, that's what they are. They just represent change. Maybe you never noticed them, and you're like, what is she even talking about? Then just ignore what I just said. Okay, so here we have two lovely, I want to go back and put the system on that. System on that, system on that. Now we have these two and we want to go to step 2, we want to eliminate. Let's just multiply what? The top one by minus 1. So here we go again. This will be minus the number of blues minus 2 times the number of greens equals minus 6. And then our B will be number of blues plus 9 times the number of greens equals 20. Cancels, that becomes positive 7 times the number of greens equals 14. John, thank you so much. Let's write our answer up here. Blues, greens, yellows. And we just got that the number of greens, I'll write it over here so I still have some room to work, equals 2. That goes right there. Now we're looking for an equation that has the greens plus one other variable, not both, and with some nice easy numbers. So I'm going to go back here. Let's take this one before we multiplied it by -1. Here's my box I'm working in. The number of blues plus 2 times the number of greens, which is 2, equals 6. That's 4. So we subtract the 4 from both sides. The number of blues equals 2. And then the third one's always the easiest because of that original quantity statement. They have to add up to 7, and so this must be 3, right? 2. Oh, yeah, I'm looking at my answer in the book. John just wrote them in a different order, so I was like, what? 2, 3, and 2, but he wrote blues, yellows, and greens, and I have blues, greens, and yellows. Yay, that's right. That's a super happy smiley face. All right, so that is lesson 111, 3 statements of equality. The first 2 look very familiar. The third one isn't all that difficult. We just have to think it through and write it as an inequality first. And then we solve by first putting the little guy into the 2 bigger ones and then eliminating the 2 bigger ones. Enjoy lesson 111. Thanks, guys.